Professor Kaisa Matmaki from University of Turku, Finland. She is a number theorist, and her recent work on distribution of multiplicative functions in short intervals is really been appreciated all over the world. And in fact, I'm happy to see that the Möbius, especially Möbius transformation, she will be talking today about the distribution of Möbius transformation in short intervals. And just to tell some of she's one of the most young, one of the most recognized number theorists, I would say, in the world at this age itself. She's very, very young and one of the most recognized one. And she has already won the Shastra Ramanujan Award in 2016. And in 2019, she was awarded the New Horizons Prize. So we're really honored to have Professor Matmaki with us today. So it's over to you, Professor Kaisa Matmaki.
Okay, thanks for the introduction and thanks for inviting me to talk here. So this will be a very general overview about things that we study in analytic number theory, such as primes and almost primes and the Möbius function. So I'm trying to make the talk quite centered. And I will start by introducing the topics. Like I will just talk a bit about the primes, and then I will discuss how primes are related to the Riemann zeta function, and then I will discuss primes in short intervals, and finally talk about so-called almost primes. And then I will move on to the Möbius function. I tell this is the Möbius function, and I will discuss the Möbius function in short intervals. And then I will be rather brief with the proof ideas, but I just describe sort of the general framework of proofs in this area of mathematics. And then I will just get back to describing, okay, what was that we had proved. Okay, so let's start with the prime numbers. So the prime numbers, I will denote them by blackboard P, and they are so 2, 3, 5, 7, and so on. And they are the natural numbers that are greater than 1 and are only divisible by 1 and themselves. So you can see the first primes here. For instance, 8 is not a prime because it's 2 times 2 times 2, and 12 is not a prime because it's 3 times 4. But if there are no divisors except 1 and the number itself, then it's a prime. And in this talk, the letter P will always be reserved for primes. When I have a P, it's a prime. And these primes have been studying for centuries, or actually for thousands of years. So Euclid, already 300 BC, saw that there are infinitely many primes. And the proof is very quick. I can do it in 3 lines. So suppose that there were only finitely many primes. Let's call them P1, P2, up to pk. So suppose that there are only k prime numbers. And then look at the product of all these prime numbers and add 1. So this number here, it's not divisible by p1 because if you divide by p1, the residue is 1. And it's not divisible by any pi because always you are left with 1 when you divide by pi. So either this is a new prime or it's divisible by a prime which is not included in the set of all primes I had. So this is a contradiction. There must be infinitely many primes. And furthermore, an important property of the primes also observed by Euclid is that every integer can be uniquely written as a product of primes. So for instance, 2022 is 2 times 3 times 337. All these 3 numbers are primes. So the primes are sort of the building blocks of the integers because you can write every integer as a product of primes. And so then the question is, are the primes really the building blocks of the integers, or are there some differences? So if you think about factoring a given integer, if you have some integer like 5,300,076, it's not easy to factor it. It takes quite a lot of time. Of course, with this size of numbers, computer can do it quickly, but by hand it takes time. And if the number is huge, then it takes a lot of time also for the computer. And on the other hand, multiplying is much easier. It's easy to do with the hand, with pen and paper, and computers can multiply huge numbers just in a very fast time. So this is completely different from building blocks. with building blocks, it's difficult to build. It takes a lot of concentration, whereas you can just do the destruction with your left hand without no problem. So I think that the Legos are a more accurate model for the primes because the building takes also time, but also the construction takes time. And well, for the more of the analogy, you need always more and more primes to construct all the integers. When you get into bigger integers, the finitely many primes are not enough, or some primes are not. You always need more and more primes in order to construct all the integers. And it's the same for the Lego bricks. The kids always want more Lego bricks. Okay, so we now know that there are infinitely many primes. The natural question is that how many primes are there? How large proportion of numbers up to x are primes? And this was answered more than 100 years ago by Hadamard and de la Vallée-Poussin independently. They saw the prime number theorem that the number of primes up to x is about the logarithmic integral of 1 over log x from 2 to x, or more concretely, it's about x over log x. So the density of the primes is about 1 over log x, or you could say informally that the probability that a given integer n is prime is about 1 over log n, because the number of primes up to x is about x over log x. And for this reason, or actually for more technical reasons, it's convenient to normalize primes by a weight log p. And so we write lambda n for the von Mangold function, which is log p if n is a prime power, and it's 0 otherwise. And the prime powers are so rare that we don't have to actually care about them. So essentially what this does is that it gives the weight log p for every prime, and it gives the weight 0 for everything else. And now this prime number theorem is equivalent to the fact that the average value of the von Mangold function is 1. If you sum it up to x, then you get about x. And the reason that we rather study this von Mangold function than the characteristic function of the primes is that it's nicely related to the Riemann zeta function, as I will next explain. So let me define the Riemann zeta function. So for a complex number s, whose real part is greater than 1, we define the Riemann zeta function by a simple series of sum of 1 over n to s. And since every number can be uniquely written as a product of primes, we can write it as an Euler product, where we take a product over primes and look at 1 plus 1 over ps and so on. And by summing this series here, it's a geometric series, we get another representation for the Riemann zeta function. And all these things converge nicely when the real part of s is greater than 1. But it's possible to analytically continue the Riemann zeta function to the whole complex plane, except that there's a pole at s equal to 1. And this zeta s is called the Riemann zeta function. And it's a famous function, in particular one of the most notorious unsolved problems in number theory, and the whole mathematics is the Riemann hypothesis, which asserts that all the non-trivial zeros of the Riemann zeta function have real part of s equal to half. So there are some trivial zeros for the zeta function, but the non-trivial zeros are those that have real part between 0 and 1. And the famous Riemann hypothesis says that all of those should have real part s equal to half. Nobody knows how to prove this. And how are the zeta function related to the primes? It comes from this Euler product. Actually, it's closely related to the fact that zeta function has an Euler product. We know that the prime number theorem, that the number of primes up to x is about x over log x, or that the average value of von Mangold is about 1, is equivalent to the fact that the Riemann zeta function doesn't have zeros at the edge of the critical strip. It doesn't have any zeros with real part of s equal to 1, so that the zeros can't be on the edge of this critical area. And on the other hand, the Riemann hypothesis that all the zeros have real part of s equal to half is equivalent to the fact that we have a very good error term in the prime number theorem, that they can calculate the number of primes or estimate the number of primes very accurately. That is that the number of primes up to x is about the logarithmic integral plus an error term of size x to half plus epsilon. Or for the von Mangold function, it's a simpler thing, that the average value of one Mann mode function is 1, and then there's a very good error term. So Riemann hypothesis is closely related to the primes, and the zeta function is closely related to the primes. But then the question is why? Why is the zeta function and the primes related to each other? So I will give sort of a quick explanation of this phenomenon. And it's based on the fact that if we look at the zeta prime over zeta, it's the same thing as the derivative of the logarithmic of zeta. And we can here, for real part of s greater than 1, we can write the zeta as the Euler product. There we have the product of the primes 1 minus 1 to 1 over p to s. And then if we derivate this, it turns out that we get the sum of the one Mann mode function divided by n to s. So just doing the derivative here. And so we say that the generating Dirichlet series of the one Mann mode function is minus zeta prime over zeta. And so this is the first important fact, related the Riemann zeta function to the one Mann mode function, and so relating it to the primes. And then if we want to look at the number of primes up to x, we use contour integration. One can prove that if we look at the integral of y to s over s in a horizontal line in the complex plane, we get 1 if this y is smaller than 1, and we get 0 otherwise. So this integral can be used to spot the condition like n is up to x. And this is what we do. If you look at the one Mann mode function up to x, that is the weighted sum of the number of primes up to x, then we can spot this condition that n is smaller than x by using this formula here, by replacing this condition that n is at most x by this formula with x over n in place of y. And this gives us the sum of the one Mann mode, and then this integral that we used for spotting the condition. And then changing the order of summation and integration, we end up having this Dirichlet series involving one Mann mode function here. So we managed to sort of relate the number of primes up to x with an integral of the zeta prime over zeta. So this is what we got. And now doing some complex analysis, moving the integration to the left, we pick up a pole at s equal to 1, and it gives us the main term x. And then if there are some further poles, then this gives some non-trivial contribution to the prime number theorem. And in particular, if there are no zeros of zeta up to with real part s greater than half, we can move the integration line to real part of s equal to half plus epsilon without meeting any poles, and that gives us the way to show that the Riemann hypothesis is equivalent to the fact that we have a good error term in the prime number theorem. And on the other hand, if we work unconditionally, we can move the integration line a little bit left from the one line, and this allows us to deduce the prime number theorem if the one line doesn't have any zeros. So this is why the zeta function and the one Mann mode function, or the primes, are related to each other. Okay, and there's also a simpler thing you can see from the Riemann zeta function. You can see just the infinitude of the primes more easily. You don't need any complex analysis really. If we write the definition of zeta function, and now if we take logs on both sides and get s 10 to 1, then we know that here is the harmonic series sum of 1 over n, and we know it diverges. So also the log of this must diverge, but it's essentially the sum of 1 over p when s tends to 1. So we get that also sum of 1 over p diverges. So this is an easy argument to see that the sum of 1 over p diverges. And this is again similar to the Legos. If the number of buildings is tending to infinity, then must also the number of bricks. So similarly, if the number of integers is tending to infinity, so must the number of primes. Okay, and then I will turn to the short intervals because that's in my title. One wants to know what happens with the prime number theorem tells us how many primes are there up to x, but what if we just take some shorter segment around x? We don't took all the primes from 1 to x, but instead we look at some segment around X. Do we still know that the density of primes in this segment is 1 over log X? And we have some information about this question. In particular, Huxley's prime number theorem that was proved 50 years ago tells us that if we look at segments of length at least x to 7 over 12 plus epsilon, then we still do have the prime number theorem in short intervals. We know that the density of primes in intervals of length at least x to 7 over 12 plus epsilon is about 1 over log X. And this again related to the zeros of the Riemann zeta function. In particular, it's based on Huxley's zero density estimate, which concerns the number n sigma t, which is the number of zeros of the Riemann zeta function that have real part of S at least sigma and the imaginary part of S at most t. And Huxley's zero density estimate gives an upper bound for the number of such zeros. And this zero density estimate allows one, using the relation between the one magnitude and the zeta prime, what zeta I showed you previously, allows one to solve the prime number theorem in short intervals. And here the 12 over 5 is closely related to this 7 over 12. So I think you have to, what you do here is you take 1 minus 1 over this number, and then you get the exponent here. So 1 over this is 5 over 12, and 1 minus it is 7 over 12, and so on. So if there's any improvement on Huxley's zero density estimate, then you immediately get an improvement also on the primes in short intervals. And this again shows how the zeros of the Riemann zeta function are closely related to the primes. But there has been no improvements, except using a sieve trick heat brown showed that one can do slightly shorter intervals. You don't have to have 7 over 12 plus epsilon, but you can have 7 over 12 minus little of 1, so very close to 7 over 12. But for 50 years, there has been no improvements, and there are still no. Except that if you don't request an asymptotic formula for the number of primes, but you are just happy with finding some primes in the intervals or positive proportion of primes, then one can do shorter intervals. So Baker, Hamann, and Binz showed 20 years ago that if you look at intervals of length x to 0.525, then you can find the correct order of magnitude of primes. So you can still find in intervals of this length that there are h over log x times a constant number of primes. But if one goes into shorter intervals, then we don't even know that there exist primes in all short intervals. If we assume Riemann hypothesis, that helps a bit. Then we know that there are primes in intervals of length x to half times log x, but it doesn't help too much actually, because unconditionally we have 0.525, and with Riemann hypothesis we get x to half times log x. So there is still, it's not so helpful here. In particular, compared to what we expect to be true. So Kramer has made a probabilistic model on primes, and it was based on the fact that the sort of probability of n being prime is 1 over log n. And based on this, we expect that all intervals of length log x to 2 plus epsilon, for instance, contain primes. So we are very far from this. Even assuming Riemann hypothesis, we have to look at intervals of length about square root of x. But we expect that intervals of length about log x squared contain primes, and log x grows much, much slower than x to half. So there's a huge gap between what we know and what we expect to be true. So perhaps we can ask an easier question, because even under Riemann hypothesis, we don't know that intervals of length x to half always contain primes. So what if we don't require that all intervals contain primes? What if we are content with hanging that almost all intervals contain primes? And for this, there's a variant of Huxley's prime number theorem, which says that we can do much shorter intervals. We can do intervals of length x to 1 over 6 plus epsilon rather than x to 7 over 12 plus epsilon, and for almost all x. And this is based on the same zero density estimate. And it has also resisted improvements. Nobody knows how to improve on this, except that one can do the heat brown trick and get plus epsilon changed to minus little of 1. And also, similarly to the all interval case, one can do a lower bound for quite a bit shorter intervals. In this case, for intervals of length x to 1/20. But again, we are quite far from what's expected to be true. It's expected that for any h tending to infinity with x, the interval of length h log x contains primes. So the density of primes is 1/log x. So if we look at intervals of length, say, log x over 2, we don't expect them to contain primes always, perhaps half of the time, or even almost always. But it's expected, and probabilistic models confirm that it's a reasonable expectation that if we look at intervals of length h log x, then they contain primes for almost all x. And as for the Legos, we mostly keep them in one room. So fortunately, there is no analog with primes in almost all short intervals. We don't have Legos almost everywhere. Okay, so conjecturally, we think that for any h tending to infinity with x, the interval of length h log x contains primes for almost all x. And there are some conditional results concerning this. Riemann hypothesis is not sufficient to obtain this. I think probably Riemann hypothesis gives us primes in almost all intervals of length log x squared. I'm not sure here. But anyway, Heatbrand has shown that if, in addition to the Riemann hypothesis, one assumes the pair correlation conjecture for the zeros of zeta, which says that the sort of the zeros don't know about each other too much, then one does get this conjecture about primes. And on the other hand, with Juri Merikoski, we have recently worked on the same question under the unlikely assumption that there are exceptional characters. So let me describe briefly our result. So L function is very similar to the Riemann zeta function, but it's twisted by a multiplicative function called the character. And in particular, we expect that the Riemann hypothesis is true also for this L function, that they don't have zeros, the real part of s greater than half, but nobody can prove this again. And also we can't rule out that they have so-called exceptional zero, a zero very close to the s equal to 1 spot. And what my theorem with Juri Merikoski says that if there exists such an exceptional zero, then almost all intervals contain the expected number of primes. But it is under the unlikely assumption that there are exceptional zeros. But now if you want to study primes in almost all intervals, you can assume that there are no exceptional zeros. That's the use of the theorem. But we do have the sort of the short interval range is the correct one, and we have it for if there is an exceptional character of modulus Q, then we have it for certain x's. But that's not the main thing I'm talking about today. So let's move on. Okay, so now I talked about primes, and the next thing on my title is almost primes. So let me explain what is an almost prime. So it's either pk number, which has at most k prime factors, or an ek number, which has exactly k prime factors. So we say that the number is an almost prime if it has a very few prime factors. And there are two different notions, either that it has at most k prime factors. In particular, if we have a p2 number, then it's a prime or a product of two primes. But if we have an e2 number, then it's a product of two primes. There's no possibility that it's a prime, but we still call it almost prime, even if it can't be a prime. And there has been quite a lot of activity on studying pk and ek numbers in short intervals because the primes are so difficult to study, or we are stuck with them. So there has been some progress on this. In particular, Teräväinen has showed that if you look at intervals of length log x to 3.51, they almost always contain an E2 number, a product of exactly two primes. So remember that for the primes, we can show that almost all intervals of length x to 1/20 contain primes. So this is much shorter interval that one can get if one looks at two primes instead of this. And actually, Joni and I are currently working on improving this, and we can probably do intervals of length log x to 2.11 instead of 3.51, but that's forthcoming thing. And on the other hand, concerning the pk numbers, Friedlander and Ivanets in their book Opera de Libro, sketch how to solve that if here we look at the best possible result that h tends to infinity as slowly as one wants, then all intervals of that hx contain 3 numbers, so products of at most 3 primes. And I have recently improved on this. I can show that almost all intervals of length h log x contain p2 numbers. So that's the best one can do in terms of pk numbers. Because of course the primes, they are numbers that have at most 1 prime factor. So that's primes themselves. And well, as an analog for Legos, there are some almost Legos by other trademarks, but I don't have experience, so I don't know if they are good approximations. For these pk and ak numbers, they are quite nice approximations, but they are genuinely easier to work with than the primes. Okay, and then let us turn to the third topic on my title, that's the Möbius function. And I will start by defining the Möbius function. So it's called the Möbius function μn, and it's -1 to k if n is a product of k distinct primes, and it's 0 otherwise. So it's 0 if n is not square free. If it has a repeated prime factor, then it's 0. And otherwise, if there are no repeated prime factors, it's -1 if the number of prime factors is odd, and it's +1 if the number of prime factors is even. And it's possible to work out the generating Dirichlet series for the Möbius function. If you look at the sum of the Möbius divided by n to s is 1 over zeta. And this already tells us that the Möbius is quite closely related to the von Mangold function, whose generating Dirichlet series was zeta minus zeta prime over zeta. And this is 1 over zeta. So they are closely related. And in particular, there are similar relations to the zeros of the zeta function for the Möbius function as there are for the primes. So the prime number theorem was equivalent to the fact that zeta has no zeros with real part of s equal to 1, but it's also equivalent to the fact that the average value of the Möbius function is 0. That about the same ways, if you look at a random integer up to x, the likelihood that it has an even number of prime factors is about the same as the likelihood that it has an odd number of prime factors. And also the Riemann hypothesis is equivalent to the fact that there is sort of cancellation then you sum of the Möbius function. And well, I don't have any Lego analogs anymore about the Möbius. Okay, so let's look what is known about Möbius in short intervals. And until about 10 years ago, the story for the Möbius function was exactly the same as for the von Mangold function. In particular, Huxley's prime number theorem was adapted to the case of the Möbius function by Motohashi and Ramachandra independently. So they saw that the Möbius function has average 0 for intervals of length x to 7 over 12 plus epsilon. So in those intervals, there's about the same number of numbers with an even number of prime factors as there are numbers with odd number of prime factors. And similarly for almost all x, it was known that the average value of the Möbius function is 0 when the interval length is at least x to 1 over 6 plus epsilon. And this second result was shown to hold for much shorter intervals, actually the interval length of h tending to infinity as slowly as you wish with x. So you can look at intervals of length h equal to log x, for instance, in my work with Maxime in 2016. And so this is different from the primes. For primes, we don't know how to improve on these results. But for the Möbius function, Maxime and I managed to go into much shorter intervals. And here we crucially use the fact that the typical n has prime factors from certain convenient intervals. And this is certainly not true for the primes because they don't have any prime factors whatsoever except for the prime itself. So this was something we thought there is a difference between studying Möbius function and the primes. And for the Möbius function, one can do much shorter intervals when one looks at the Möbius function in almost all intervals. And then a natural question that nobody asked for a few years was whether one can do a similar thing for all intervals. And recently, Joni Teräväinen and I did prove such a result. So we managed to improve this 7/12, which had been there since 1970s. We managed to show that for all intervals of length x to 0.55, the Möbius function has cancellation. In this length of intervals, about the same number of integers has even an odd number of prime factors. And note here that 7/12 is 0.5833, so we improve it by 0.0333, but well, that doesn't sound too much, but it should be taken into account that even assuming the Riemann hypothesis, we can't go below 1/2, so we do get quite a bit closer to this barrier here. Okay, so let's now turn to discussing what's sort of how to prove these things. So I have been describing several things. I will go back to my overline here. So I've been discussing the primes and how they're related to the zeta function. That's more sort of to give some background about things. And then I discuss results about primes in short intervals, like Huxley's prime number theorem, which says that we get an asymptotic formula for the number of primes in intervals of length x to 7/12. And almost all intervals where we get an asymptotic formula in almost all intervals of length x to 1/6. And here I hinted a bit about the proofs too. I told you that it can be proved using the zero density estimates due to Huxley. But there's also an alternative proof of these things related to Dirichlet polynomials, and I will mention that soon. And then I went on to talk about almost primes, where we have these pk numbers that are products of at most k primes, and these ek numbers that are products of exactly k primes. And for this, we have several results in much shorter intervals than for the primes, that we can find ek numbers or pk numbers. And then, so this different things that one can prove. Also for the Möbius function, one can study Möbius function in short intervals, in almost all short intervals. So by this work with the maxim, we can get into very short intervals. And on the other hand, we can do the all interval result a bit better than the zero density estimates of Huxley. But there's some common themes in all these proofs. If you look at primes or almost primes or the Möbius function, and you are studying them in short intervals or doing something else, in general, when one tries to prove something about the primes or the Möbius function, there's a general strategy for doing this. And this is what I'm going to describe next. What is the general strategy that one often uses in analytic number theory when one wants to catch the primes or study the Möbius function? So that's my aim next. Okay, so I'm here. So if one wants to prove something about the prime numbers or about the Möbius function or about the almost primes, then often the proof is divided into two steps. There's a combinatorial step first, and then there's an analytic step. And in the combinatorial step, one uses a combinatorial identity or sieve method in order to reduce the problem to so-called type 1 and type 2 sums. And in the analytic step, we estimate these sums. So this is the rough idea in the proofs. So the proofs I already described, like based on the Huxley's zero density estimate, they don't follow this line. They don't work like this, but it would be possible to do the primes in short intervals, the Huxley's result on primes in short intervals and primes in almost all intervals also in this setup. It would be possible to do first a combinatorial step and then an analytic step. And this has actually been done by Heath-Brown already a few decades ago. Okay, so let me describe a bit more first the combinatorial step and then the analytic step. So for the combinatorial step, there are various identities or sieves that one can use. And one of the most basic ones is Vaughan's identity. And it's a way of writing a sum of the primes. So this is the sum of one Monod function weighted by some alpha n, the sequence we are interested in. We can write it in a, well, at first sight, a more complicated form. So this is an identity which is true, and it can be checked by perhaps the easiest way is to compare the generating Dirichlet series on each side. So this actually an identity pointwise. One can do just look at alpha n. So one Monod n equals the sum of BC equaling n with B log C plus minus the sum of ABC equaling n, and so on, so on. So this is an identity. And the first question is, why is this helpful? What's the point of this identity? And the point is that this splits our original sum about the one Monod function. It splits into two different types of sums. We call them type 1 and type 2 sums. So we call a sum a type 1 sum if it has a shape like this, where we look at the products of m and n, and we have this alpha m n as before, but we have am instead of one Monod n. And this has the advantage here, but there are no, this doesn't depend on the long variable n anymore. So m is at most x to 1 over 3. We have this am here, and we have alpha mn, but there is no bn appearing here. So one instance, in our case, we are interested in short intervals. So we can take this alpha n to be the characteristic function of the short interval from, say, x to x plus h. So all these sums, the alphas disappear. And instead of summing from x to 2x, we sum from x to x plus h. And then we have here, for instance, a short sum from x to x plus h of mn and only am here. And I think I will soon explain why this is helpful. So the sum here is more or less a type 1 sum, because here we have b up to x to 1 over 3, and it has an unknown coefficient mu b. And the c has a very smooth coefficient log c, so it's almost as there is no coefficient. And this, on the other hand, is either of type 2 form, where we have a genuine bilinear form with m and n both being between x to 1 over 3 and x to 2 over 3. So all of these sums can be written in either of these forms. So the advantage of type 1 sums is that there's a smooth variable n, where we don't have any coefficient, instead we have just am. And the advantage of type 2 sum is that we have a real bilinear structure here. And then in the analytic step, we want to estimate these type 1 and type 2 sums. And then it depends on what we are interested in, what's our sequence. That's what we do. And before going into that, I should mention that there's a similar identity for the Möbius function. It can be also written as a type 1 and type 2 sums, just like the one Monod function. And also, there are various different identities one can use. Instead of Vaughan's identity, one can use Heath-Brown's identity, which is a bit more flexible in terms of the sums that one gets, than Vaughan's identity. And then there are various sieve methods that one can use. So for detecting almost primes, one can use, say, Richard sieve, but also for the primes, one can use Harman's sieve, where you do a similar decomposition, but you can throw away some parts if you just want a lower bound. Anyway, in the analytic step, one wants to estimate these type 1 and type 2 sums. And for instance, that's sorting. Then we can use Dirichlet polynomial through Perron's formula. So in this case, the type 2 sum, for instance, looks like this. It's the sum of mn between x and x plus h, am, bn. And by contour integration that I described when I showed how the primes are related to the zeta function, we can do a similar contour integration here to spot this condition that mn is between x and x plus h, we can spot this by contour integration, and we end up studying the mean value of corresponding Dirichlet polynomials, like here. And these mean values can be estimated through mean and large value results for Dirichlet polynomials. And it seems I don't have it on my slides. I should have put it here. But if we have here, in this case, we have a type 1 sum, then there is no coefficient like bn here. It's just 1 in place of bn for type 1 sums. And in this case, we can simply first put the sum over m outside, and then sum inside over n between x over m and x plus h over m, and sum once, because in case of type 1 sums, they equal to 1. And then we can evaluate this sum over n's as h times m. And we actually get this identity if the support of AMs is at most h. So this explains why the type 1 sums are easier. Often one can put sort of sum inside, put the sum over n inside, and then there is not much to be summed, just the sum of alpha m n's. And if it's something simple like the characteristic function of the short interval, then one can do the sum if m is not too big. So this is what we want to do in the analytic step. And it depends. If you look at something else than the short intervals, then you do the analytic step, something else. You can't relate it to the Dirichlet polynomials. Perhaps you can use some Kusterman sums or something like that, but it's sort of, it all boils down into understanding the type 1 and type 2 sums in the analytic step. And so what's our combinatorial steps and analytic steps in the different theorems I described? So for the theorem of almost primes in almost all short intervals, which was showing that almost all intervals of length h log x contain P2 numbers, there is first the combinatorial tool, which is 3 Hertz weighted sieve with the beta sieve. That's what I use for that. And this allows me to reduce just to type 1 sums. So if you are interested in pk numbers, you can, it suffices to deal with type 1 sums. You don't have to be able to deal with the type 2 sums. But the problem is that if you only use the type 1 sums, you can never catch the primes due to the parity phenomenon. And on the other hand, in the problem for Möbius in short intervals, with Untitled, where we studied the sum of the Möbius function in intervals of length x to 0.55 plus epsilon, the combinatorial step, we had actually 2 combinatorial steps. We first used Ramarez identity, which allows one to take out a very small prime factor. And after that, we used the heat Brown identity to the rest. So the new trick in our paper was to use the Ramarez identity first. And in my work with Maxime Razive on Möbius function in almost all short intervals, in the combinatorial step, we used Ramarez identity, but we used it in several different ranges. So we took out prime factors of different sizes using it. And then in the analytic step in these works, concerning the almost primes in almost all short intervals, the analytic step was Kusterman sums, estimate for Kusterman sums. I used some Dishor's Ivanets bounds for Kusterman sums, but actually being a bit more, doing it a bit differently, one could have just used the well bound for the Kusterman sums to get a sufficiently good type 1 estimate. And on the other hand, for this problem on Möbius in short intervals, we did exactly what I described before. We turned the problem into a problem on Dirichlet polynomials, and then we used known large and mean value theorems for the Dirichlet polynomials in order to deal with the type 1 and type 2 sums, and actually also type 1/2 sums coming from the Heat-Franz identity. Okay, so let's now return once more to the theorems. So the theorem concerning the P2 numbers said that for almost all x, the interval of length h log x contains P2 numbers. So the conjecture says that these intervals almost always contain primes, but this conjecture is known only assuming some further conjectures like the Riemann hypothesis and the Bell correlation conjecture together, or by assuming the unlikely conjecture that there are infinitely many secret zeros. But unconditionally, we can only reach P2 numbers. And this is because if you look at these intervals, there's absolutely no proper type 2 information available. We can only have type 1 information there. And on the other hand, the theorem concerning Möbius in all intervals, Joni and I were able to show that in intervals of length x to 0.55 plus epsilon, the Möbius function has cancellation. So this improves on Huxley's 50-year-old result concerning intervals of length 7, 0, 12, or Mutahassi and Ramahandra's variant of Huxley's prime number theorem. And again, here, the sort of the limit of all the methods we know is at x to half, because Riemann hypothesis only gets us down to x to half, but it's expected that the Möbius function has cancellation in very, very short intervals. And actually the work of Maxime and I show that in almost all intervals of length, of any length tending to infinity, the Möbius function does have cancellation. So for the almost all intervals, one can always do much better than for all intervals. So for instance, for the P2 numbers in all intervals, I think the best result is that all intervals of length x to 0.4 something contain P2 numbers. It's better than for the primes, but it's still quite far from what's expected to be true. And I should say that one can use similar methods for other problems as well. In particular, this setup that Joni and I have for the Möbius function is quite flexible. In particular, it works for other multiplicative functions like divisor functions. And it also works for the products of exactly two primes, in the sense that we can show an asymptotic formula for the number of products of exactly two primes in these short intervals. One could show the existence of products of exactly two primes in shorter intervals. In particular, already the Baker-Harman-Pinch result concerning primes in all intervals of length x to 0.525 implies the existence of products of two primes, but the point is that we can show an asymptotic formula, the correct asymptotic formula for the number of products of exactly two primes in these short intervals of length x to 0.55 plus epsilon. And also one could study, for instance, the sums of two squares and so on. So it's quite flexible. One just needs some sort of combinatorial decomposition of the heat-bound type in order to do this. For this, I'm not sure. So if there is a variant that I think somebody is actually working at the moment is what if instead of short intervals, one looked at arithmetic progressions. So there's sort of analog between arithmetic progressions and short intervals in these things. Anyway, that's actually all I wanted to say today. Thanks.
Thank you so much, Professor Tamaki. Wonderful. And now, is there any question from the audience in the seminar room?
So, hi, ma'am. I hope you can hear me. Hello, can you hear me?
It's a bit difficult. It's sort of.
Hello. Now is it okay?
Okay, let's try.
Okay. So, what is the expected bound on this on the short sums of Möbius functions? Even under RH, you're saying we can say let's say big O of root h or something, right? I don't exactly remember, but can we do better than that? It seems that the expected bound on the short sums, the expressage of mu of n, then what is the expectation that of those sums, of the size of those?
So I'm actually not sure. I think that if one makes a probabilistic model, then one probably thinks that in all intervals of length about log x, there should be cancellation in the Möbius function. I think that's, but not in all intervals of length as short as we have in Maxime, because the length of the interval can tend to infinity as slowly as one wishes. But if one look at probabilistically, then one would expect that there are some intervals which are pretty long there. The Möbius function takes 1 for all the square root numbers. So I think it's about the log x is the limit that one can hope to have a result for all intervals.
Okay, ma'am. And you were saying that for almost all x, you will have cancellations, right? So I presume it's like you will have something like if you take the number of x for which you have a certain prime, that will the natural density will go to 1, let's say. So do we know how is there an effective version to say that almost all x, like
so the result I have here is for all x. This result with the Ravine, it works for all x. But my work where the h is very small, it is for almost all x, and we do have a bound what we mean by almost all. In particular, in part 2 of our paper, the almost all is like with the x over h to epsilon exceptions. So if you look at intervals of length h, then we can show that almost all of them, there is cancellation, and the number of exceptions is about x divided by h to epsilon or something like this.
Okay, so you have an arbitrarily small power saving on that. So it's like x plus big O of x to the power 1 minus epsilon.
So for the exceptional set, we can have a good saving by our methods, but for the little of h term here, the saving is small. It's like a small power of log x that we can never save with a method. The method never saves more than 1 over log x in the bound for the average of the Möbius function, because it's based on the fact that we have to use these numbers with a small prime factor. We can never deal with the primes, and the density of primes is 1 over log x, and we can't do anything about them. So that's why our error term is always quite not so good.
Okay, ma'am. Thank you.
Yeah, no problem.
Any other question here? Yes, so we can move on to the online participants. If there is any question, please unmute yourself and you can ask Professor Mathema. Yeah, I don't see anything in the chat also. So let us thank Professor Mathema.